but I need to spend some time to explain this definition. Yeah, it's not easy to understand. Yeah. Yeah. Let me change the pen color here. Because this definition is very abstract. Yeah. Yeah. So let me explain the meaning here. Big O notation. We have 6 asymptotic notations. Yeah. But for this class, we mainly use 2 of them. Yeah. Big O, big theta. Yeah. Next one, big theta. These 2. All right. So first, let me go through the definition quickly. Then I explain the meaning here. For a given function g of n, yeah, the notation big O of g of n, this whole notation represents the set of functions. You know the set concept in math theory, set. Okay? Yeah, so set. A set of functions. Yeah. Each element is a function. F of n. Yeah. That satisfy the following condition. There exists some positive constant c. Yeah. Yeah. Here, the positive constant, we want to use it to estimate f function. How do we estimate? This is the way to estimate. C multiple of g, we use this function. G function, we fix it. Yeah. We use g function to characterize this set notation, big O of g of n. Yeah. So that g function. And the g function, usually we like to use relatively simple functions. Yeah. Simple function, how simple they are. So the g function, usually we use 2 simple, relatively simple functions. First one is the power function. For example, n to the k, okay, power function. Second function, log function. Yeah, yeah, log function. Yeah, yeah. We use these 2 functions to form g function. Yeah, but we can use product. Okay, sum, product. Yeah, combination, certain combination of these 2 functions to form g function. Yeah. All right. So then the condition, positive constant c and some non-negative integer n0. Non-negative, yeah. I need to explain the role of this n0, n0. So non-negative integer n0, yeah, such that this inequality holds. F of n less than or equal to c multiple of g of n. Hold, the important part for or n greater or equal to n0, the condition. Yeah. All right, so now I touch all the important pieces here. Yeah. All right. So here I want to explain the importance of this non-negative integer n0. Why it is so important. Yeah. Here, remember, this notation we want to use to measure efficiency function of our algorithms. Efficiency function. F of n, that's efficiency function. Yeah. G of n, relatively simple. We want to do comparison. Yeah. F of n, yeah. How fast? Because usually f of n is relatively complicated functions. Yeah. So we want to simplify it. Yeah. Too complicated. Okay. How do we simplify it? G function. G function is the simplified version. Used to measure f function. Yeah. How to measure constant multiple? C constant, positive constant multiple measure. And a big O notation, we only look at the upper bound. We do not look at the lower bound. So here you can see there is no lower bound. Left-hand side, yeah, so not important. Okay, lower bound, Here, not important, so we do not look at it. Okay? The next one, big theta, we will look at both upper bound and lower bound. Yeah. But here, we are only interested in the upper bound. Yeah. All right. Then, non-negative integer n0. So here first, you can see we have freedom to choose this n0. We can choose. Okay? Yeah. Not given. So it's not given. Yeah. For a specific algorithm, we can choose what is the n0 we want to use here. Yeah. So you can even choose 1 million if you like. Okay? Very large, 1 million. No problem. Yeah. But as soon as you choose it, then you should fix it. Yeah. Then fix it. Yeah. After we choose it, we fix it. Yeah. Then we look at this inequality. It must be true, yeah, because this n is variable, right? We can change n variable. So when you change n variable, you cannot change n0 anymore. Okay? After you fix it, after you choose it, fix it, then when you change n value, making it larger and larger, you cannot change this n0 anymore. Okay? You have to fix it. Yeah. All right. Then here, let me use. So because I forget bring my remote control, so I have to use the keys. After you select it, it must be fixed. Here. Yeah. And here, there is another. Yeah. So let me explain that meaning. There. Yeah. So here, let me use my. Oops. Just my stick. Yeah. So here, regarding this n greater or equal to n0, this condition, there is another commonly used expression when n is sufficiently large. Yeah. Sometimes people write. Sometimes people do not write this n0 explicitly. Okay? Sometimes people skip this n0. People just say replace this. Yeah. So sometimes it's like sometimes people replace this whole part by this sentence when n is sufficiently large. Yeah. When you see that, yeah, so you can understand this way. There is some non-zero constant n0 for all n greater or equal to n0. Yeah, because only when n greater or equal to n0 we say it's sufficiently large here. Yeah. Otherwise, because sufficiently large, people may argue how large is sufficiently large, right? Yeah. How large? Because it's subjective. It's not objective. How large is sufficiently large? Yeah. For some question, probably 1 is sufficiently large. Yeah. For some question, 1 is sufficiently large. But for some questions, 1 million, still not sufficiently large. Yeah. 1 million, not large enough. Yeah. You need to use a larger number for n0. Yeah. Yeah. Based on your problem. Okay. So how large is n0 based on your problem? Yeah. All right. Then, let me draw a graph. Yeah. The graph, let's look at this one. F function, this is f function, okay, f of n, the curve. Yeah. If we draw the graph of f function, yeah. So then the relatively simple g function, the g function, if we do not multiply appropriate constant c, the g function probably will be below f function. Yeah, but it's okay. We can use a constant multiple c to control the position of g function. Okay, after we choose certain appropriate c constant, then the graph will raise it to use it to as a ceiling, as a as a ceiling on top of the graph of f function. Then another part. Look at the vertical bar here. The vertical bar. Okay. Dot dashed line at position n0. Okay. Look at that. At the left-hand side of this vertical dashed line, doesn't matter. Look at this. Doesn't matter. Why doesn't matter? Doesn't matter here. It means f function, the graph of f function above c of g function above or below doesn't matter. Okay? Doesn't matter. So this the state here not important. Doesn't matter. Okay? Doesn't matter. Okay? All right. So now you know the importance of this line. Only the n value past this dashed line, the comparison matters. The comparison matters. Before this line, doesn't matter. Okay? Before this line, f function is not bounded by c multiple of g function, not important. Okay? That's the special property of this definition. Here, let me explain. So you may ask me why we do like this? Why this part doesn't matter? Here, let me explain a little bit. The reason it doesn't matter is that's the early stage, right? Early stage for the n value. So when we do experiments, we choose relatively small n values. So here you can see the performance of the efficiency function when n relatively small is not important when we compare algorithm efficiency. So our main focus is on the efficiency function when the n value very large. Very large. When n value is very large, then we worry about, if it is too slow or not. Okay? When n value is relatively small, not important. Even if it's, so you do comparison not that good, not important. That's the meaning. That's the meaning. So here I want to explain why we don't worry about relatively small n, the function value when n is relatively small. All right. So here the main issue is when n relatively small, when we do experiment, so usually the function value, f function value is not very large. F function, the number of comparisons also relatively small. So then, when you write a computer program, you need to do setup, right? You need to do preparation, prepare your data. You need to do a lot of work to set up, right? In order to run the program. Then, when you do setup, you spend a lot of time on the overhead part. So we call it overhead. Okay. The setup part, you need to do preparation work. You need to use certain amount of time to set up, to do preparation. Okay? But when n is small, the overhead part dominates your f function. We spend a lot of time in the overhead part. This value relatively small. So the overhead part dominates the function value. Okay? So that's why larger, small, not important. Okay? The overhead part dominates. All right? But when you increase the n value, it becomes larger and larger. F function grows. Okay? F function grows larger and larger. Overhead keeps the same. Overhead does not change. Okay? Overhead does not change. Then f function value dominates the overhead part. Okay? Overhead part, comparing with the function function meaningful work. The function part, that's the the main work. Yeah, yeah. It could be ignored. Yeah, the overhead part, the percentage becomes 1%, 0.1%, 0.0001% when you increase n. Yeah, it could be ignored. So when n is very large, the overhead part could be ignored. Okay? All right. So now, with that understanding, you can comfortably feel this part doesn't matter. This part mainly related to the overhead part. Okay? We should not look at the part containing the, when the overhead part takes most of the response time. Okay? Yeah, so that's this part. That part we should, skip it. We should skip that part. Okay? That's the reason it doesn't matter. Okay? All right. Only when n sufficiently large, passing this line, that means sufficiently large. Okay? So here I spent a lot of time trying to explain the, main points of this concept. Because this is the most important concept here. From now on, after we have the basic understanding of this concept, then later we will use this terminology to measure our algorithm efficiency. Yeah. All right. Next, big omega, big omega lower bound. The language, almost the same. The only difference is at the lower bound. Yeah, so then I can go through quickly. Okay, so here you can see the language almost the same. Yeah, the difference here, first, notation big omega. Yeah, all right. Yeah, then we just use the C multiple of G function to measure the lower bound of F function. Okay? Yeah. Only the change from the graph, just look at the lower bound. Okay? After we multiply G function by certain constant C, you see the curve below the curve of F function after n pass this line. Dash the line at n0. Yeah, doesn't matter before n0. Okay? Yeah. The same idea as the previous one. Yeah. So one upper bound, one lower bound. Yeah. But this lower bound case we rarely used. Yeah. Although here we have the notation asymptotic notation, but for the remaining of the class we rarely use this lower bound version, asymptotic notation. But we use this big theta notation, both lower bound, upper bound. Yeah. So here, so we combine the previous two definition here, but this time we need to choose C1 and C2. Yeah. And both lower bound, upper bound. Yeah. Like this. Yeah. Yeah. Sufficiently large. Yeah. The same as before. Yeah. So this one. Sometimes we want to use this one. Okay, both lower bound, upper bound. Yeah, both lower bound, upper bound. So here you can see upper bound more important. Yeah, upper bound more important, but lower bound sometimes we want to include it. Sometimes we want to include it, so we use the big theta notation. But many times we do not want to include it. Yeah, it's already enough to use upper bound. Then we just use the big O notation. Yeah. Yeah. All right, so for this class, you will see most of the time we use big O of G of n or big theta of G of n. Okay, so you just focus on these two. Yeah. All right. Yeah. So that's the definition part. Yeah. Any question? Yeah. About the definition? Yeah. Yeah. Then this one. In order to understand the definition better, so I want to give you a few examples. Yeah. And these examples also prepare you for our first homework assignment. Yeah. So this weekend, actually after today's class, Wednesday, after our Wednesday's class, I need to assign you our homework number 1, that big assignment, preparing for the midterm, that one. Yeah. Yeah. Because already third week, in the middle of the third week, so I need to give you our big, long assignment. Yeah. And these example here, yeah, help you solve some of the homework questions. Yeah. So it's important. Yeah. All right. Asymptotic notations. Yeah. All right. So we do some understanding related to the definition. Yeah. The first one, very simple. Yeah. First one, show our f function n plus 2. So simple. n plus 2 constant. Okay. But we want to show this function belongs to big theta of n function. Yeah. That's simple. Okay. Yeah. So g function is just the n. G function. Yeah. Big theta, we know its meaning upper bound, lower bound, right? Yeah. C1, C2. Yeah. C1 upper bound, C2 lower bound. Yeah. So how to for this type of function here, I mainly use to help you understand asymptotic notation better. Yeah. In the homework, I do not ask you to show like this. Okay. Yeah. So here for understanding. Yeah. Yeah. All right. So here to show there are 2 ways. Yeah. Yeah. There are 2 ways we can use to show n plus 2. Yeah. Oh, yeah. Here I need to attach this because I need to control the slide. Yeah. All right. The first way, the limit way. Yeah. Yeah. We can use the limit. Yeah. Lower down. Yeah. Remember, we can calculate the limit. Yeah. So here. All right. The first way, remember the ratio of f function g function, the limit way. Okay. All right. So the first way, let's consider the limit n goes to infinity. Numerator f function n plus 2. Oh. Denominator g function. Oh. Let's calculate the ratio of f function over g function when n goes to infinity. Do you know how to calculate it? It's very simple. How to calculate it? How much is the value here? Calculus. Okay? Calculus. Yeah. So let's do simplification a little bit. Another step to let you see better. N over n, that's 1, right? 2 over n. This fraction. When n goes to infinity, what's the value? N goes to...
Are you talking about the value of the entire expression? Or
yeah, entire.
Oh,
entire. 1. Oh, yeah. So, I need to... Yeah, sorry. I need to give you more space here. Yeah, because, give you a full screen here. Yeah. And here... to make you feel better. Yeah. Yeah. So the answer is 1. Yeah, because 2 over n, when n goes to infinity, it's 0. Second term 0. The first term 1. Yeah. So here, this 1 is non-zero constant, right? Yeah. So it's positive, non-zero constant. Yeah. So remember, when the ratio of f function over g function equals non-zero constant when n goes to infinity, that corresponds to this big theta case, upper bound, lower bound case. Yeah? So if you calculate the limit of the ratio and your answer is a non-zero or positive constant. Yeah, let's say positive constant, yeah, because we never have the negative case. Positive constant. Then you can make your conclusion f function belongs to big theta of g function. That's the first method, okay? Limit method. Second method, we need to use the definition of big theta. Upper bound and lower bound, okay? Yeah, so here. Let's write f function first. Yeah. We need to find a constant, C1 constant for upper bound part and a C2 constant for lower bound part. Yeah. All right. Yeah, n plus 2, we need to find a constant multiple of g function n. Here, g of C2, we just use 1 times n. We know n plus 2 greater than n. Yeah, so that C2 is 1. Yeah, here, because it's simple, we can see it. We can see it quickly. Yeah, all right. When you need to specify the range, when is this inequality true? Yeah. Here, and because we only consider n greater or equal to 0, right? Yeah. When n greater or equal to 0, this inequality is true. Okay? Yeah. So this 0 is our n0. Yeah, n0. Yeah. All right. And the C2 here, C2 is 1. C2 is 1. Okay, all right. Yeah. Then, upper bound. How do we get upper bound? So we replace the constant m by, constant 2 by n, and we want to increase the result. Increase the result. Yeah. So n plus n, 2n. 2n. Yeah. Yeah. But the inequality upper bound is true. This is true. Yeah. Less than or equal to 2n. This inequality is true when n greater or equal to 2. Yeah. If n equals 1, this is not true, right? If n equals 1, this inequality is not true. So we need to specify the range where n greater or equal to 2. So this time n0 is 2. n0 is 2. Okay? Yeah. All right. And C1 is 2. Here, 2n. C1 is 2. Okay? C1 is 2. So we find C1, C2 non-zero, positive constant C1, C2, and at the same time, we need to choose appropriate n0. Okay? n0 from these two range expressions. We have two range expressions. Yeah. In order to make both side inequality true, we choose a larger n0 value. Larger n0 value. Okay? All right. So n0 is 2. C1 constant, we find it. C2 constant, we find it. And n0, yeah, so that line, that vertical line, we also find it. So if you want to use definition to prove this conclusion, this result, definition, you need to tell me, what is your C1, what is your C2, and what is your n0. Yeah. After you give me these three numbers, then you can make the conclusion. Yeah. So from the first example, you can see there are two methods, the limit method and the definition method. A definition method, you need to do a little more work, right? A little more work, yeah. So limit method, a little easier. Usually a little easier. Limit method, yeah. All right, so that's the first example. The second example, yeah, let me erase this. Second example, oh, yeah. Yeah, so this time we only look at the lower bound, yeah. Big omega. Yeah. Lower bound, so that means we need to choose n cubed greater or equal to constant multiple of suitable n square n squared, g function n squared. This time we choose c equals 1. C equals 1. We can see this inequality holds when n greater or equal to 0. Yeah. N greater or equal to 0. Because we only consider n integers, right? So 0, 1, 2, 3. We do not consider n equals 0.1, right? Yeah, if you plug in 0.1, this inequality does not hold, right? Yeah, because our n values always integers. Yeah, so we do not worry about non-integer values. Yeah, yeah. So here the c is 1. Yeah. n0 is 0. Yeah. So that's simple. Yeah. Okay. Yeah. All right. This example. Yeah. This example also two methods: limit method and definition method. Yeah. So here, let me show you these two. Yeah. All right. Let me look at the time. Yeah. All right. Limit method. Yeah. Yeah. Let me leave the limit method for your own practice. Okay. Yeah, because it's not hard. For your own practice. Yeah. Here I only do the definition method: upper bound, lower bound. Yeah. All right. Yeah. So lower bound first. Yeah. We just use, n cubed. Yeah. We ignore plus 2. We make the function value smaller, right? Yeah. After we eliminate, cross out plus 2, the function value becomes smaller. Yeah. So then we take cube. Yeah. So here you can see, lower bound side is easy. So we find a constant. Yeah. The range for this inequality holds n greater or equal to 0. Yeah. Upper bound, this time upper bound. Yeah. Upper bound. Yeah. Still, based on our previous example, we replace 2 by n, and I try to make it larger, but when you replace like this, you require n greater or equal to 2. N greater or equal to 2. Okay? Yeah. So now you take cube on 2n, so you get an cubed. So your C1 constant is 8. Now, in this way, your C1 constant becomes 8. Yeah. C2 1, C1 8. Yeah. And then n0 equals 2. Yeah. So for this cube case, you can see this is the relatively simple way to do it. Yeah. Yeah. But there is a bad way. Yeah, there is a bad way. Yeah, because before I assign this kind of questions. Yeah. And some students did in a very complicated way. Yeah. So here I want to point it out. Yeah, do not do it that way. So those students, they expand this formula. Why get out? So by accident, why get out? All right. Yeah. All right. All right. So those students, they use the polynomial expansion formula, or binomial formula we learned before. So they expand it first. They write expansion like n cubed plus 3, so 6 n squared plus 12n plus 8. So they do the expansion first. But the problem is after you do the expansion like that, in order to find appropriate constant multiple of n cubed to be the upper bound, that's too hard, right? Much harder, okay? Yeah, so here, I want to let you know in the situation like this, do not do the expansion. If you do the expansion, then it's too hard. How do you get constant multiple of n cubed to, to upper bound this function? It's hard to see it, right? Very hard to see it, okay? Yeah. So do not do it this way. Yeah. So let's find upper bound before we raise to third power. Before we do that, we find upper bound first. Then it's much easier. Yeah. Yeah, because I remember I assigned a version, not a cube, fifth power. Yeah. I assigned a fifth power question to a student. Those students still do the expansion, but fifth power. Much more complicated than this one. Okay? Then it's extremely hard to find the upper bound constant multiple of n to the fifth. Right? So don't go that way. Okay? Yeah. So use this way. Yeah. Because this way, even I put 100, the exponent 100 number here, still easy, right? 100, just 2 to the 100th, okay? But if those students do the expansion 100, can you handle it? Nobody can handle it, okay? 100 expansion, yeah. All right, so that's the, main problem, yeah. Next question, this time log function. Show that log of n belongs to little of n. So this time we use the notation little o, okay? Yeah. Do you still remember the meaning of little o here? A little bit? Yeah. Remember at the beginning when we talk about asymptotic notation, we have several cases. There is one, it's little o, okay? Yeah. Little o actually it means because when you use the little o, you can only use the limit way. You can only use the limit way. Okay? So we need to consider the limit n goes to infinity, log of n over n. We want to show this limit equals 0. Okay? We want to show. Yeah. If you can show this limit is true, then your conclusion is log function belongs to little of n. Yeah. Okay, all right. Yeah. Let me show it. Actually, I remember I showed you similar question before. The older version is n over log function. Yeah, not the log function over n. Yeah. But here, we switch. Yeah. And remember we used L'Hopital's law. Okay? Yeah. All right. So let me quickly go through that. L'Hopital's law. Yeah. Yeah. Here, for the L'Hopital's law, remember, we need to take the derivative. But when you take the derivative, we want to use the consecutive variable x, not discrete variable n. So we need to change to that continuous variable version. Then we can take derivative. Before we take derivative, we need to check if it is infinity over infinity indeterminate form, right? Infinity over infinity indeterminate form. Remember, if you look at questions in quiz number 2. Yep. I assign you quiz number 2. There is one question. If we can apply L'Hopital's rule all the time, right? Yeah, here, before we apply, we need to check if it's infinity over infinity. Yeah. If it's not, you cannot apply L'Hopital's rule, right? If it's not infinity over infinity, then you cannot apply L'Hopital's rule. Yeah. Here we can, because when x goes to infinity, log function goes to infinity. Okay? When x goes to infinity, the denominator function also goes to infinity. So it's infinity over infinity form. Yeah. So we're fine. So we can apply the L'Hopital's rule. So let's take derivative. Numerator, denominator. Numerator, denominator. Okay? Numerator, derivative, certain formula. So we copy the formula. Yeah, that's the formula. Okay? Denominator, 1. Power function, derivative here, it's 1. Yeah. After simplification, let's do the simplification. Yeah. After simplification, yeah, n over natural log of a, remember the hidden base, yes, here. Yeah. Our assumption, when we use log, the general log function, we use some hidden base a greater than 1. Yeah. All right. 1 over denominator function natural log of a, this is a constant. Yeah. This constant times x. Yeah. Because a is positive. A is greater than 1. So this natural log of a is positive, right? It's a positive constant. Yeah. All right. Now, the question. Let me ask you a question. Now, this is a ratio. Numerator function, it's a constant 1 over denominator function. The question, can we apply L'Hopital's rule again here? Is it legal applying L'Hopital's rule here? Is it legal? Yeah. Look at that. Is it infinity over infinity? No, it's not. So it's illegal. Okay? So at this place, you cannot apply L'Hopital's rule because it's not infinity over infinity, indeterminate form. Okay? Constant, it's 1. Determinate, it's determinate, 1. Okay? Yeah. So we just take the limit directly. Okay? When x goes to infinity, yeah, constant, positive constant times infinity number. So you know what is the limit. Yeah. 1 over denominator could be very large. Okay? Infinitely large denominator. Yeah. So the limit is 0. If the limit is 0, can we say log function belongs to little o? Yeah? Yeah. Although here it's a continuous version, remember the limit, when we use the limit, x approaches to infinity in arbitrary way, so we just take discrete value way, approaches infinity, right? So we can go back from the continuous version to discrete version immediately. Yeah? Because definition of the limit allows us to go to infinity in arbitrary way. Yeah. That is one way to go to infinity, right? Yeah. 1, 2, 3, that's a one specific way to go to infinity. So it's fine. We can do it. Yeah. So the result, we get this little o proof. Yeah. Little o proof. Yeah. Although for this class, I do not give you any proof question. Okay? Yeah. But here, the reason I show you a few proof questions to help you understand the concept. Yeah. Yeah. All right. Next question. Yeah. This time, we need to show that n to the d, this d number, it's a positive number. Yeah. This function, yeah, it's a power function. Yeah. Power function. Okay, n to the d. Yeah. Belongs to little of a of n. D So here, d greater or equal to 1. So although he d greater or equal to 1, actually we can consider d just any positive number. Any positive number. It's true. Yeah. It's true. Okay? Yeah. All right. But here, the d greater or equal to 1, the reason I use here, this version, first I want to consider integer d greater or equal to 1. Integer d. Yeah, actually d is not necessarily integer, right? Yeah. That d, n to the d, that d, 2.5. N to the 2.5. Still okay. Yeah, not necessarily integer. But for this question, in order to show this result, I want to take L'Hopital's rule, then I want to use the integer case, the integer case. L'Hopital's rule. Okay. All right. Yeah. So here. Yeah. So let's use the limit way to show it. Yeah. So let's take the ratio of these two functions. Yeah, integer. Later, we may want to remove the integer assumption. Yeah. First, let's assume the integer, positive integer. So let's consider this continuous variable version of the ratio of the two functions. Yeah. Oh yeah, jumping too fast. Yeah. All right. So yeah, let me. Yeah. Before we jump, can we check first the condition? Is it legal to apply L'Hopital's rule here? Is it legal to apply L'Hopital's rule here? Why is it?
It's a continuous variable and a multi-continuous
Yeah. Another important point, infinity over infinity indeterminate form. Yeah. When x goes to infinity, numerator goes to infinity, denominator also goes to infinity. Yeah. Never forget to check this infinity over infinity indeterminate form. The question. Yeah. Yeah, there are other. Oh yeah. So in math, there are many more. Yeah, good question. Many more. For example, 0 over 0, right? 1 to the infinity, right? 1 to the 0, many. Infinity to the 0, and the 0 to the infinity. In math, there are many more. All right, but for this class, we only have one. Okay. This class, no sense for other possibilities, right? There is no sense. Yeah. So for only this class, okay, we only consider infinity over infinity. Yeah, good question. Yeah. Yeah. But in math, so many cases. Yeah. Yeah. Probably you can list 10 cases. Yeah. Because there is another case. Yeah. Infinity minus infinity. Is it indeterminate? Infinity minus infinity could also be infinite, any possible values, right? Yeah. Indeterminate. Yeah. Infinity minus infinity, right? So many different cases. Yeah. Probably you can get 10 cases. Yeah. 10 cases. Okay? Yeah. All right. Yeah. All right. Yeah. But for this class, only focus on this single one. Yeah. That's good. Good enough. Yeah. All right. Then we can take derivative, numerator, denominator. Yeah. So like that. Okay. Yeah. Here I assume you know the formula, or at least you can find these two formulas. Okay. Yeah. Then after this, can we see the limit immediately? Yeah. If not, yeah. So if we cannot see the limit, then we look at the expression. It's still infinity over infinity. If d is greater or equal to 1, or greater than 1, okay? If d is greater than 1, it is still infinity over infinity determinate form, right? Yeah. That means we can apply L'Hopital's rule another round. Yeah? One more round. Yeah? If it's infinity over infinity, we can keep applying L'Hopital's rule all the way down to the non-determinate form. Yeah. We stop when the form becomes non-determinate. Okay? Oh, sorry, becomes determinate. Indeterminate. Yeah, in is not. Yeah. Becomes determinate. So we can stop. So let's apply L'Hopital's rule another round. If d greater than 2, we apply another round. Yeah. Keep going like this all the way down the last one, d round. We apply L'Hopital's rule d times. So x to the d minus d, it's 0. X to the 0, it's 1. So the numerator becomes a constant. Now it's not indeterminate form. Okay? Yeah. So we can stop. We can stop. But this time, other than the constant, look at the exponential function a to the x. When x goes to infinity, then it is 0. It is 0. Okay? Yeah. So this question, so you can see, we need to apply L'Hopital's rule several times. Okay. Yeah. Okay. All right. Yeah. So then another question. Yeah. After this question, then before we move to the next example, I like to let you consider a special case here. Now, after we prove it, okay, this time we want to modify the d condition. Yeah, because at this, in our proof, we assume d is a positive integer greater or equal to 1. Yeah. But after we prove it, here, we rigorously prove it. Yeah. Now I want to change it to the condition d greater than 0. D is any positive integer, not necessary. D is any positive number, not necessary integer. Not necessary integer. Okay? Yeah. This time. Yeah. So the question, if I remove the integer assumption, question, how to prove it? Yeah. Yeah. This time the proof. The proof should be different. Yeah. So how do we handle that difference? Yeah. All right. So here, because here it's a good example, I want to show you. Oh, sorry. Oh, microphone. Some microphone thing. Yeah. Yeah. All right. Yeah. So let me just put here. Yeah. So here I use one. Yeah. So yeah. Before we take a break, we have a few minutes. Yeah. So let me use a few minutes before the break to explain this point. Yeah. In problem solving, so here I want to use this example to explain one important idea in problem solving. In the general problem solving, when we solve one particular problem, sometimes that problem is relatively hard. Yeah. If we want to solve it directly, it is hard. Yeah. Here it's like d positive non-integer value. Yeah. We treat as a relatively hard question. Yeah. To solve that, one commonly used method is, first, let's do not solve the original problem directly. Let's find approximate, or let's find a simplified version of the original problem. We can modify the original problem to a simpler version. How about that? Let's modify the original problem to get a simpler version to solve first. That idea. Approximate idea. Let's approximate original problem, not exact original problem. We find an approximate version, but that approximate version is simpler. Okay? It's simpler. Here, the idea. let's approximate original version D, not necessary integer. Let's consider integer case first. How about that? Yeah. D is integer phase because that's simpler. Yeah. Then when D is integer, it's simpler, we solve it. Here, that's the solution for the integer version, right? We solve it. Yeah. All right. After you solve a simpler version, integer version, simpler, then this time we consider the original version, non-integer version. How much is the difference? When we go back to the original version, we want to compare the target version and our approximate version. There is a difference, right? Yeah, there is a difference. How do we handle the difference? How do we fill the gap? There is a gap, okay? So we need to do some work to fill the gap, to fix that gap. Yeah. So here, that idea. Yeah. Let's do some work. Yeah. Just to bridge the gap. There, we need to, bridge. Yeah. Make a bridge. Bridge the gap. Yeah. This idea. Yeah. In general problem solving, this idea is very useful. So here, this example, I want to show you that idea. Okay. Yeah. All right. Yeah. So I still let me just use a few. 2 or 3 minutes, so before we take a break. Yeah. How to bridge that gap. So here, let me show you. Now, if D is non-integer, can we find two other adjacent integer, let's say K? Can we find two other adjacent integer K such that D greater or equal to K and less than K plus 1? So D is between two of the adjacent integers. We can always find those K, right? Yeah. Yeah. D falls between two of the adjacent integers. Yeah. Okay, all right. But for the two of the adjacent integers, integer case, we already show it, right? We have the result for the integer case. Let's use the integer case as the stepstone to solve the non-integer D case. How about that? Yeah. So that idea is, very effective in real-world problem solving. Now let me write the critical step. You can see how do we bridge the gap between integer, non-integer. Okay, all right. Yeah. This time, because our goal, we want to consider n to the D over a to the n, right? Yeah. N to the D. Can we write it as n to the D over n to the K plus 1 times, yeah. So here, let me write this inequality here, use space. D between K and K plus 1. So, and I use space here. N to the K plus 1 over a to the n. Can we write like that? Yeah? See? Yeah? Cancellation, right? Cancellation, okay? So the same expression, right? Cancellation. But when you write it in this way, can you see the relationship much better? Okay? Because the first one, when you compare the ratio D less than K plus 1, so the denominator increases faster than the numerator, right? So this first fraction less than 1, right? Yeah. The first one, less than 1, okay? Yeah. Denominator greater than numerator, right? Yeah. So look at here, D less than K plus 1. So the numerator less than denominator, okay? So that ratio less than 1. All right. The second one, it's an integer. We can apply the integer version that goes to 0, right? Yeah. This time, K plus 1, it's an integer. Integer version, can we get goes to 0? The ratio goes to 0 when n goes to infinity. Yeah. So a number less than 1 multiply number goes to 0, it also goes to 0, right? Yeah. So here you can see with this kind of manipulation, yeah, special manipulation, we can bridge the gap. Non-integer version, integer version, we find a way to bridge the gap. Yeah. Try to think about this problem-solving technique. Yeah. And we can make this general. Right? So here's just special example, but this idea could be general, right? Yeah. You solve a simpler approximate version, then find a way to bridge the gap. Okay? Then you solve the whole problem. All right, let's take a break. And